Welcome to another MathCast. In this episode we're going to be taking a look at another volume problem. We're going to be sort of a very simple basic problem in this case using disk method. We're given the function sine x cosine x and asked to evaluate that function on the interval from 0 to pi halves by rotating it around the x-axis. So I have the graph here already, ready for us to go. We're going to write on top of it. That should always be your first step in doing these problems, is you should be able to come up with a graph either on your calculator or drawn out by hand that looks just as good as this one. So on the interval from 0 to pi halves, if I look at my y values, sine of pi halves, as we recall, is 1, but cosine of pi halves is 0, so altogether this is 0, meaning that this point is pi halves. And this point is, of course, x equal to 0. And the area that we're interested in is the area in the curve that's bounded by the curve sine x cosine x and also bounded by the x-axis. And we're going to try to rotate it about the x-axis. So let me put my little rotation symbol in here. This is the figure that we're wanting to look at. Basically, once this curve is rotated around, you'd get something symmetric down here, and so the volume that's traced out would be something like a top, sort of an old-fashioned top that you'd spin on a table. And so that's sort of the area, or excuse me, the volume that we're trying to find. In order to do that, if I'm applying disk method, remember that disk method uses the radius, which is essentially the function on the interval of investigation. So it would be the volume from 0 to pi halves, and I would have pi times the radius squared, and then I'm integrating with respect to x. Now, why am I integrating with respect to x? Well, remember, I'm always considering rectangles here. So if I consider an example of a rectangle on this region, so something, let's say, like that, then the idea is this rectangle varies depending on what x value it takes between 0 and pi halves. The height of the rectangle is always governed by the function f of x, which in this case is sine x cosine x. So applying that here, the radius is the integral from 0 to pi halves of pi times the radius, which is sine x cosine x. And that's only valid from 0 to pi halves, so we are indeed talking about this curve being traced out, squared dx. Now why is it pi r squared? Well, this is because the cross sections are circles, and the area of a circle, as we all know, is pi r squared. So we're basically taking this volume and we're going to slice it into a bunch of really thin pieces. Those thin pieces in the limit, in other words, as delta x goes to 0, in the limit this rectangle becomes a line and the area becomes a circle. Well, if I tried to eventually evaluate this integral, we've done integrals like this semester, we would end up with something that looks like this. And remember, the best way of evaluating this is to use your half-angle identities. Now, since this isn't a lesson on integration, at least not for integrating things like this, I'm just going to go ahead and tell you what the answer is. I would expect you to work this out on your own to make sure you can get it, but the answer we wind up with here is pi squared 16ths. Remember, the half-angle identity for cosine is 1 plus cosine 2x divided by 2, and the half-angle identity for sine is 1 minus cosine 2x over 2. So those should be the two identities that you're going to use for this problem. All right, we're going to look at several more of these. We've got at least 3 more videos planned. We're going to talk about integrating with respect to y at some point. We're also going to talk about washer method and Shell's method. So stay tuned for those videos.